Good evening, friends. This is Anirban, and this is the next blog post I want to make. And today, I want to continue the discussion on computer vision with some discussion on unsupervised methods like image clustering. Last session, I talked about deep learning and training deep learning models in various ways, and which is essentially a supervised machine learning problem. But many a times we come to a situation in industry where labels are not available. So I was given such a problem in my last assignment where I was working for a global company, and I was asked to cluster the image vectors coming from some biological molecules. I cannot say more details than that. So, how do we go about clustering these images? What's the best way? So, one of the things we have to keep in mind while doing such exercises for industry is that what I've learned is that the response time is very, very important. I mean, industry normally we don't get lots of time to research on all different things and come back. We want to do something quick, a quick prototype which shows the business yes the results can be obtained using this technology, and then we go for a more detailed solution. So I'd like to show what how we can do that. So as an example, I'm taking the MNIST image data set, right? So here is my collab notebook, and as can be seen, I am downloading the MNIST dataset from the TF Keras datasets, and I'm taking the test images, just a sample 1,000 images from the test images, and I'll try to cluster it and see the results how it comes. So we can say we have 10,000 images, 28 by 28. We know these are black and white images with the handwritten digits. Let's take about 1,000 images from them, and let's linearize this because I want the images as vector. So since it's 28 by 28, I'm linearizing it as a vector dimension, a vector with dimension 784. So I can check up one image by displaying it on the screen. So let's say I take the position index position 300 or any other position, and I check the image as well as the label coming with the image. Yes, we have labels here. The labels can work as a verification mechanism if our clustering is working right over here. There is no other use in actual scenario. You have to remember we'll not get labels because the labels are not there. We're doing clustering, right? So we can see yes, we have the images correct. We can see the images. Let's take one more example, and we can try to plot that. We can see that the images are there and the labels are also matching. So one quick way of clustering which I used and gave me good results is basically not doing any coding, no coding approach, right? So what I did is I took these images, I took the linearized, vectorized form of these images, and what we can do is put these into TSV files, right? So I'm just putting this to TSV files, these data frames, which has a linearized form of the vectors, and also another TSV file which has the label data. So that is the metadata. We call it the metadata, and I just download this from the file section into my downloads directory. And what we can do is this is the quickest way, and it gave good results when I showed it to my lead. He said, "Oh, this is good. I like the results and continue the project." So that's why I'm showing this initially. So when we go to projector.tensorflow.org, we can just upload our own data, and you have to wait a little bit because I think it has some default data. So we upload. It says that you can load data from your computer. One is a TSV file of vectors. So this file is nothing but each sample has one row of vectors, and the label or the metadata file is nothing but each row has the label associated with that sample. So if there are 1,000 vectors, there are 1,000 rows. in the TSV file of vectors, and there are 1,000 rows in the TSV file of metadata. So I choose the file, which is in my case this one. Let's see what I named it here. I named it test image data.tsv, test lab label data.tsv. So let me choose that. Test image data.tsv is my data for the images, and test label data.tsv is my data file for labels. So I upload this, and that's it. It takes up the data, and it will basically try to cluster, and you can choose your dimensional reduction techniques. You can choose whether you want in 3 dimensions or 2 dimensions and all that. So let's see how the cluster looks like. You can ignore this because it has taken up our data now. So let's use a color map based on the label. I have 10 uh, labels, right? Because from 1 to 10, and this is basically we are validating our cluster with these labels. In actuality, we know there won't be any clusters. So by default, it selects PCA for dimensional reduction, and by default it does in three axis XYZ in 3 dimensional. Let's do it in 2 dimensional, and let's see how this cluster looks like. I would like to see in t-SNE first, and you can see the clusters forming, and you can see that each color basically represents, again it's in 3D by default, and we can see that these uh, dark brown ones are one, and few sevens are also mixed up with them, but the sevens are orange ones and they are mixed up in the same cluster. We can see here these violet ones are all twos, right? So the cluster formation is correct. It's still going on the t-SNE computation, and you can see that the cluster is changing in shape as the computation goes on, the iterations go on. We can reduce it, we can change these parameters, right? We can see the sevens clustering here, we can see the threes clustering here, right? The sixes, all the greens are the sixes, and there is few inaccuracies, right? We can see some mixture of zeros over here in the same cluster, but more or less it looks good. I think this t-SNE iterations, there should be some way to control that. We can stop it at some point. We can make it 2D also in t-SNE, and we can see the clusters on a 2D plane. So maybe after about 1,000 iterations, we can stop it, right? So we can see that these sevens are in the color orangish. The brown colors are basically all the ones. So it displays basically, the labels when you put the cursor on that. We can do UMAP clustering as well, UMAP dimension reduction as well, and see the clusters. Again, by default, it's on 3 dimension, and you can see the clusters here. So you can see the clusters are forming quite good. Again, here all these twos are in one location, they're clustered. The ones are spread out over a region. One can see the cluster in 3 dimensions. One can spherize the data if one wants, and it will be spherized, and you can see that also. So this is a quick way of clustering, and one can keep on experimenting with 2D, 3D, changing the neighbors using t-SNE or PCA, right? All kinds of things, and see the clusters uh, very quickly on this tool called projector.tensorflow.org. Just wanted to say that it gave me good results, and I was able to show the initial clustering. And then once we progress more, we can do the clustering on our notebook with more finer control, right? So I'll come back to this deep learning things, but let me show how we can do the same clustering using our code. So we have this feature vector from the test images that we have. It is a feature vector of 1000 by 1000 samples with 784 dimension vectors each. So we can do a PCA on this with n components equal to 2 because we want to visualize on 2 dimensions. And then we can use the SciPy library to find out the clusters and to find out the cluster centroids, right? The SciPy library VQ. So we can do that. So basically, once we do this, centroids variance equal to k means, we supply the feature vector and say we want 10 clusters. So k means one of the important things that we need to know the number of clusters which you want to get in advance. That's needed in k means, right? And we can get the code, which means the cluster index and the distance of that point from the centroid, using this method called VQ from the SciPy library. So you can see here that I am importing SciPy cluster VQ import, right? All methods from the SciPy cluster VQ, and so this has the k-means and everything. So once we do that, we can then plot it. We can see the clusters here with the cluster centroids in red color in a different symbol, and each cluster belonging to each level in a different color. So we can see that, and we can basically, these are the cluster, based on the cluster codes the colors are given, not based on that label. It is the cluster codes 1 to 10. And so one of the important things here is using k-means is we can do the clustering on the reduced dimensions, or it is a much more accurate thing to do the clustering on the original dimension. So here we can do the clustering on the original dimensions, features test. Mhm. So we can do that, and right. So the advantage here, I'm doing the clustering on the original data without doing any dimension reduction, right? So if I see my centroids, there are 10 centroids because I've given k equal to 10, and each of these centroids has a dimension of 784. So now just for visualization, I do the dimension reduction. This is a much more scientific way to do the clustering on the data as is and then do the visualization. So let's look at that result. Yes, so we can see the clusters. We can also use tsne for the dimension reduction. So with two components, and so k-means is one of the most basic clustering algorithms and can give good results in most cases. And I think one should try out k-means. But it's important, another aspect, k-means depends on the feature vector. So here, as a feature vector, we are taking the image pixel intensities. Whatever the image data we have, we are taking that data as is as a feature vector. So I have a 784 linearized array for each image, and that is my feature vector. And that is what tsne is giving the cluster labels, and we can check up how the labels are for uh, one of the clusters. So let's say I find out all the indexes from this data where the code is 0, right? So we can see these are the index positions where the code is 0, and we can see what kind of image we get from any one of these. So let's say I check position 34, which is occurring here, the 34th position, and let's see that image, visualize that image. It's a 7. Let's take 41st position. Again, it's a 7. Let's take this another one, 262. So this verification is based on the labels, as one can understand. In actuality, labels won't be there. So it is a business who has to verify whether these clusters are correct and making sense to them when we get the outputs of this cluster. So we can see there are some inaccuracies. Mostly these are all 7s, but there are some 9s also in the same cluster. So this one became a 9. Let's see one more example. Again, mostly 7s, 1 or 2 9s are mixed. So the cluster is good, but not fully accurate, right? And we can check with the other code numbers or other different clusters. So this is the first cluster that got formed. If we change this code equal to something else, we'll get different clusters, and we can check it, check the labels for that, how uniform they are. Now, this is one way, one straight cut way where we take the image data as the feature vector and feed it to k-means. But there is a better way to featureize the data, the image data, before introducing it to a clustering algorithm like k-means. And what is that? So what we can do is we can utilize deep learning over here, and we can basically use a feature extractor from a pre-trained deep learning model, let's say Inception v3. It could be any model. I'm taking Inception v3. I'm giving input shape as 75 75 3. Why 75? Because that's the minimum possible with the Inception v3 network, and my image size is by default, I'm getting the image data set is 28 by 28. So I don't want to go for a much higher image size, because I have to resize this image anyway by introducing zero padding and all that, right? So I take 75 by 73. I say include top equal to false. That's fine. I take weights equal to imagine8, and layers.trainable is false anyway, right? So what I can do is I can say my last layer is a pre-trained model.get layer, and give the layer name over here, mixed 8. So if we print out the layer names for this deep learning model, we can see all the layer names, and this is the last layer, mixed 8, and I'm taking the output from the last layer dot output. And what we can now do is, since it is a convolutional network, it will be a volume. So we can flatten that. So we can say layers.flatten that last output. And once we do that, we can connect a dense layer of 1024 nodes and a ReLU activation. Now, the important thing to notice here is I'm using a deep learning pre-trained model like the Inception v3, but I'm not doing any prediction. I don't have any labels. That's a beautiful thing about it. So I create a model from this model, pre-trained model, and I basically then do a model.compile, and with a categorical cross entropy loss and a learning rate. But I'm not going to do any model.train, right? So what I do is I create the feature vector by doing a model.predict, and before doing the model.predict, I have to resize the images. So that's why I say input to model, which is a resized form of the test images. So let's see how this we do this resize. I think some who have seen my first blog post will remember the little bit of discussion I did on the resizing. So this is my target size, 75 by 75 width and height, because that's what the Inception v3 takes at minimum. And so I resize the image, And basically I take a sample image, let's say a test image which is at index 300. I run this method, load resized image, and check it out. Test images. Okay, let's see. Okay, that's because I have already reshaped that data. I need the test images as is in the 28 by 28 format. Yeah. So that is what I need. So I ran this, I downloaded the data again, and now I do the resizing. So I see that initially when I do a Keras pre-processing image to array, I get a array 28 by 28 by 1. There's one channel here, and the resized image after doing this process is a 75 by 75 by 1. But here it's very important that I'm doing a kind of zero padding to the image, because my target size is higher than the image size, right? That's what we had a discussion, and that should work better rather than distorting the image to a higher size, right? So we should visualize that. So we do a we can plot this resized image and see how it looks. So we can see that the same pore we are seeing as the image, original image, but it is now of dimension 75 by 78. This line I think is not needed, right? So now that I have done this, basically I need to do this for the entire set of 1,000 images. So I need to keep on iterating through them and resize them in the same way. There is one other thing I'm doing here is converting the images from grayscale to RGB. Why it is being done? Because as we can see, this Inception V3 takes images of three channels and not just one channel. So if I supply one channel image, it will not work. So TensorFlow has provided a method called grayscale to RGB, tf.image dot grayscale to RGB. I'm passing my resized image to that. The only small thing I was facing a problem is it will not accept this image array, though it's supposed to. So we just do a convert to tensor before feeding it to this method. So we run this in a loop so that the resizing is done for all the images in my array, and the images are also converted to a three channel image, although it's a grayscale image. Same information will be copied in the three channels. So we can check out for any one element of the array how is this looking. So we can see 75 by 75 by 3 if I take the first position in the array. Now this is actually a list. I'm taking the first position of the list, because if I say np resized image add dot shape, it will tell me that a list cannot have a list object has no attribute of shape, because I created this here and I am appending to that the resized images, right? So this is becoming a list. I created a list, so that's why I can check the first element of the list, and that's an array, right? I said image to array, it gave me an array, and I resized that image using the load resized image method, which is coming from here. It is basically converting the image to an image object from the array, getting the height and width, and then this image object is basically it is sending to resize image method. What the resize image method is doing, it is using the pill image ops expand method to put the padding, the zero padding around the image. So the area where there is no information, I'm just putting zero padding instead of blowing up the image, right? And then this resized image array is what I'm sending back in the load resized image method as a result. So that is what is coming here, and so that is what is happening now. This I need to convert to an array to send to TensorFlow predict method, because TensorFlow is expecting a array which is of dimension 75 75 by 3 each element, and the sample element is a sample dimension, number of samples is the first. as we know, it's generally represented by none 75, 75, 3, right? So we need to do that. So I'm doing a np.as array and converting this list to a proper array. So now I have 10,000 75, 75, 3 images, and I've created this model already. So I do a features test is model.predict. Now this is the thing that I am not doing this model.predict to predict something and predict the class of an image or something like that. No, here I am doing this model.predict to create a feature vector from this image array, and that's what this will give me. I think I didn't choose the runtime as GPU. That's a bad thing I did. I should have. Might have to wait a little bit. At end of it, I should get a features vector which is of 1024 dimensions, because I'm using the this last dense layer with 1024 nodes. So it is going to extract the features from this deep learning model, whatever way it has been trained, and that will be my feature vector for which will be fed to the k-means. This is important because k-means relies on the feature vector, and same is not true about spectral clustering, which I'll show next. In spectral clustering, uh, it relies on the distance between the samples, the Euclidean distance, and this distance can be any distance measure. So we create eigenvectors from those distance matrix, and then we do the k-means on that. So we got the features a vector from the deep learning model, extract the features, and now we can do the k-means in the same way, but instead of the features, I use the features test. So here in the k-means, I will use the features test and use that going forward. So I use the features before doing the dimension reduction. As I was saying, I could have done the dimension reduction and then clustered it. It is always better to do the clustering on the original feature vector and then do the dimension reduction for visualization. So I'm using the SciPy library here to do the clustering. Since there are 1024 dimensions now, it's taking a little more time. And finally, I expect to get a centroids with shape 10 by 1024 now, because those that is the dimension of my feature vector. Let's see how that comes. It is going to take some time because I didn't choose a GPU, but basically, so TensorFlow is optimized to use the GPU. Then one more thing, when I got this data set for my project, I took a reduced sample and showed the initial results. But when the project kicked off, there were like 150,000 samples, and when we have that many samples, it doesn't run on normal CPU systems. It has to utilize the GPU, and for that I use the NVIDIA Rapids library to do the k-means and also to handle the data. So I use CUDF from the NVIDIA Rapids library and the CUML for the k-means, right? So I'm not using that here because it's not that big a data set. So now I do the clustering on this dimension reduction on this cluster data with 10 clusters, and I can see the centroids are of 1024 shape. So now I brought it down to 2 dimensions. I can see the centroids, I can see the everything with 2 dimensions because I have done a PCA transformation over here. And now I can plot this here and let's see how that looks. So we can see the cluster appearance changes. And this is supposed to be a more accurate cluster than the previous one, right? We can use tsne on this data, which is a featureized vector from the deep learning model. and we can cluster, we can give the t-SNE output as an input to the k-means algorithm, and we can see how that changes the appearance of the clustering. So these are the different colors for the different clusters, as we can see. We can use UMAP also over here. I have used UMAP in my project because that was supposed to be more accurate in those kind of data where the image data is derived from microscopic pictures of molecules, which is required for the research of the scientific community. t-SNE is actually also implemented in NVIDIA Rapids, I think, and one can check it out. And using that with a GPU runtime will speed this up a lot because this is only 1,000 samples. In actuality, we may get much more. We may get 50,000 samples or 100,000 samples, and that time this will become a lot of. It will take a lot of time. It will not be very effective. Still waiting for that. Once the results come, we'll have to just plot it and check it out how it looks different from the. Okay, now it has come. So once I have done the dimension reduction using t-SNE, I'm doing a k-means clustering, and then I am plotting the results over here. So we can see the clusters look much better now. You can see the cluster centroids and the clusters forming, and right. So each of these colors actually label the in, for the different cluster indexes, and one can check out right how these clusters are making sense because we have the labels here, although we don't need a lot of business expertise here, right? So we can check that out. Now the other type of clustering I wanted to talk about is the spectral clustering. Spectral clustering, actually, I have learned this concept, I must mention, from this book called Computer Vision, Programming Computer Vision with Python from O'Reilly Books. This is a book. And the spectral clustering, the advantage is it depends on the Euclidean distance of the features. So we may take the features as the features which are coming out from the image itself. We need not do a featureization. So I'll go back to this and take the features from the original image because it only relies on the distance between the images. So any distance measure is fine because it will take a Euclidean vector of that. So I'll go back here. I'll not use that. So I'll flatten this, and that will be my feature vector for this exercise. Right, 1000 by 784. So now what I do is in spectral clustering is I first have to create a Euclidean distance matrix from the feature vector. So I do that Euclidean distance matrix, and I see. So I have 10,000 vectors over here. Let me see. Oh, it's only 1,000. So there's a mismatch here. I mean, we can do features here itself. X variable I had written somewhere, it's not needed. It's basically it's saying give me the number of samples, where n is the number of samples. Then we create a Laplacian matrix, which is basically this is the formula for that. and then compute the eigenvectors of that Laplacian matrix. The Laplacian matrix is given, one can read up this book I showed. We do the sum of this distance matrix, right, for each row, and once we do the sum, we create a diagonal matrix where this diagonal is 1 by square root of that row sum, and we then take an identity matrix, right, of dimension n, and this Laplacian matrix is given by this formula I minus np dot dot product of d into np dot dot product of S and D, where S is the Euclidean distance matrix and D is this diagonal matrix which we obtained here. So once we do that, we can create the eigenvectors from this Laplacian matrix, and then we can create feature vector with two components, and then this feature vector we feed it to k-means. K-means create this, and we can then plot the clusters. You can see the clusters here very nicely. So spectral clustering, k-means clustering, there is also hierarchical clustering. I mean, I didn't talk about it, but spectral clustering, k-means clustering can work good in most cases. And so we should understand the differences between these technologies and use it accordingly. That's what I was trying to show. For k-means, the feature vector is very, very important because the clustering relies on that. If we are using directly k-means, and we might need to extract the features of mm, the images by using a deep learning pre-trained model, and here the possibilities are limitless. We can use a inception v3, we can use a vg16, anything, and we can basically take any layer as the last layer. We can take mix 7 also, the layer last but one layer, that's also possible. And we can check out for all these scenarios how the when we extract the features in different ways, how this cluster is looking, and get it verified by business. In this case, I can verify because I have the labels. So I know I can check if the clusters, 10 clusters are there. I know there are 10 labels, so I put k equal to 10, and I can check it up. But in actual scenario, when we the situation that I was talking about, the images of the molecules, there it is a business which verifies the clusters are coming okay or not, and we showed that to business and they liked it. Not only that, the another important requirement I remember was that the clusters cannot have more than 10 to 15 samples in one cluster. Now, if I have 100,000 samples, it's very difficult. We cannot do that, right? So what we had to do is two levels of clustering or three levels of clustering. That is, we create a cluster and we take the elements of one cluster, the samples, and cluster it again, so that we reduce the cluster size by that way. And finally we give to business, and they check these molecules and see and verify whether these molecules are actually similar in property. And if that is so, then this purpose is served. And in actual scenario, to get the similar molecules, what I heard, it is a very time consuming affair and takes a lot of time. So here is where we use a deep learning model to do a model.predict and get the feature vector of size 1024 dimensions, and use that feature vector as an input to the clustering algorithm like k-means, and got good results. We can also use the image data as is and the plain image vector data and use a spectral clustering, because the spectral clustering depends on the Euclidean distance matrix, and any distance matrix will work over there. It could be Euclidean distance or any other distance matrix between our images, right, will work there, because we are creating the eigenvectors from the Laplacian matrix, and from those eigenvectors we are deriving the feature vectors. So clustering is one of my favorite areas because you can see the colorful results. You can verify that. One of the samples which one can practice, I remember, is the flower data set from Kaggle. One can Google up and get that data, flower data set Kaggle. So there you will have about thousands of pictures of various flowers, and you will have the flower names over there as also as part of the labels, and one can cluster this and see whether it is really the similar flowers are coming in the same cluster. That's one quick verification, and one can use different types of dimension reduction techniques, different ways of featureizing this image data before feeding to the clustering algorithm. So thanks. I hope that was good, because I used it in one project to good results and got appreciation from business. So that's why I thought of sharing this. Thank you so much. Thanks all for viewing this.